Jack is one of our GIS experts working for our MAHSA project, and he's been helping me a lot with this GIS courses that we'll be giving to our partners in India and Pakistan. Jack, the floor is yours.
Thanks, Estee, and thank you to everyone else who has given talks today. They're all really, really interesting, and I hope you found them interesting too. And it's great to see so many participants in our GIS clinic. And hopefully in the next 45-50 minutes, you learn something about QGIS. As Azadeh said, my name's Jack Tomaney, and I work on the MAHSA project. I'm quite involved in the GIS and remote sensing side of the project, and I recognize a few names from some previous trainings that we've done, which will be similar to what we're going to be doing today. So for the next about 45-50 minutes, I'm going to be talking. And this is going to be split up into two parts, really. First, I'm going to do a bit of a presentation. And the previous talks have focused more, kind of shown what we can do with GIS in archaeology, but I'm going to be focusing more on how we actually use it ourselves and some of the key concepts that are important to be able to do this. So, the overview I'm going to talk about first. I'm going to briefly talk about what is GIS, which I think we probably all know now after the previous talks. I'm then going to run through some key concepts, talk about some data types. I'll then talk a bit about coordinate reference systems and why they're important. And then I will briefly touch on what kind of GIS software there are. And I'll kind of reiterate what Azadeh said, that this is kind of a very beginner session. So it's really aimed at people who have never used GIS before. So if you have used GIS, this might be a good reminder of some of these concepts and how to use QGIS. Okay, so firstly, what is GIS? So when people think about GIS, they usually think that it's essentially a computer mapping system, which is in fact true, but it's also a lot more than that, as we've seen throughout this morning. And try to give a good definition of GIS, a simple definition. I'd say it's a computerized system that's designed for the following things, which is capturing, storing, analyzing, managing, and presenting spatially referenced data. A good way to understand what GIS is and the way the data is used is by breaking down the acronym of GIS. So the G is the geographic, which is essentially the where. So it's a really key word in the technology, because the data that we use in GIS and the data that you will see on a map will always have a location within a reference system. So this is a representation of a location in the real world, which we call spatial data. The I, or the information component, this refers to the informational database that is associated with the where component or the location. So this data is usually in the form of tables or attributes, and it can generally be defined as additional information about the spatial features. This is often characteristics of the spatial features, which can then be used to provide further insights into that given location. So essentially, if the G is the where, tells us where something is, the I tells us what that thing is. And the S, so the system component, this is what ties the G and the I systems segments together. And this ensures that a GIS is not just a set of graphics floating around in cyberspace, but that the attributes are always linked to the mapped feature. So to give an example of how these three parts come together in GIS, in a very basic example, let's say we take a school. This is just an example of a school. In a GIS, this school will have spatial data associated with it, or a location within a reference system. So this could be in the form of coordinates, so latitude and longitude, but it could also be in other forms that the GIS is able to read. So you can see at the top here, we have the spatial data part for this school, which is the latitude and longitude. So its location within a specific reference system. Additional information, such as the name of the school, the level of education, the number of students, or really any characteristic that we could add about the school, is saved as the attribute data. So this is the I part, the information part. And the system part of GIS is what ties these two things together and makes this data useful for analysis. But how is this kind of different to a normal map? Is GIS just a normal map? Well, like a normal map, GIS shows the location of features, but that's kind of really where it ends. Traditional maps, such as road maps, they're static in nature. So they're essentially a fixed spatial snapshot of one point in time. And we can only really relay the information that is physically shown on that map. However, GIS maps are the integration of data and maps together. They're interactive, they're layered, they're changeable, and they're analyzable. Many different types of data can be included or removed within a GIS, and analysis can be performed upon the spatial and the information sections of that data. So the analysis that can be done with all the different spatial data can really be used to help people make better decisions, to visualize patterns that may not be obvious at first, which we have actually seen in quite a lot of the examples earlier today. GIS really operates on many different levels. So as I've said, in its most basic level, it's used for just making static maps. But a more complex level of GIS is used for advanced analysis of spatial data through the use of tools that help to explore and relate seemingly unrelated data, helping to understand spatial patterns and processes, known as geospatial analysis. It is really a complex subject, and its applications and outputs are used in many, many different sectors. I've just put a few here, I think, from transport to engineering to telecommunications, environmental management, of course, archaeology, really any kind of, any subject that has a locational aspect to it, GIS can be useful to be used. And it's important to say that most people have interacted or used a GIS or the product of a GIS before, maybe without even knowing it. For example, if you've ever used Google Maps to find the best route between yourself and a location, you're essentially using the product of a GIS to do that. Okay, I'm now going to touch on a few of the key concepts that you should have in mind when using GIS. And then the main data types that you will use as a beginner, and some of the ones that we will use in the practical session a bit later on. Okay, so the first concept I'm going to talk about is spatial location. So it's probably already clear that one of the most important aspects of GIS is the geography that the data has, or its spatial location. I've already mentioned a few times about the concept of the data having a locational place within a reference system. And this is very key within GIS. So it's important to quickly explain what that is. So in mapping and GIS, we use a consistent framework of set locations on the Earth within which data can be referenced to using numbers. The numbers that we reference these to are called coordinates. And therefore, we call this framework a coordinate reference system. By using a coordinate reference system of north-south lines, so longitude, as you can see on the bottom image there, and east-west lines, known as latitude, which you can see on the top image there. So applying those to the Earth, we can give every place on Earth a distinct numerical pair of coordinates, which we can then assign to the data in our GIS. So we know where it is on the Earth. It sounds simple, but it does get a bit more complicated, and I'm going to come back to this a bit later in the presentation. So what types of data can be used within a GIS and plotted onto this coordinate reference system? Well, essentially, and when we're starting out with GIS, there are two main formats in which spatial data is used in GIS, and these are raster and vector, which again have been mentioned quite a few times in the previous presentations. We're going to be using both of these in the practical session after this presentation, and it's important to know the differences between the two. So first, I'm going to look at vector data in a bit more detail. So vector data is essentially graphics that are comprised of vertices and paths defined by coordinates. They provide a way to represent the real-world features individually within the GIS environment, each vector feature can store attribute information about that feature that it's representing, such as the school example I mentioned earlier. They're made up of coordinates, and vector data can be one of three types. So you can see those here. So they're either points, lines, or polygons. And there's also many different types of files that vector data can be saved in. I've put here that the most common format is a shapefile. That might be the one that, as a beginner, you have heard of. And this is comprised of, at minimum, 4 different files. It can sometimes be more than that. And those files all work together in a GIS to display your vector data. There are a lot more different file formats, and shapefile is kind of becoming slightly less used now. You may have noticed some ones such as GeoPackage or KML, if you've ever used Google Earth, or GeoJSON, and each different type of file is kind of more commonly used for a different purpose. But we're going to focus on shapefiles because this is maybe the most common format. So to look at these different types of vector data in more detail, points. So points are a single pair of coordinate values. They're used when features are too small to be represented as polygons. For example, you can't see city boundary lines on a global scale. So in this case, maps often use points to display these city locations. Same with archaeological sites, and we've seen this quite a lot earlier, that sometimes you'll be making a map that will be 50 kilometers in area, and a small site may be too small to be represented by its actual boundaries. So instead, we put a point there to know that that is its general location. So these are made up of an XY coordinate pair. Next, we have lines. These are made by a sequence of coordinate pairs, which define coordinate pair defining points, through which the line is drawn. Essentially, we're connecting the dots to form a line. Lines usually represent features that are linear in nature, for example, rivers, roads, pipelines, things such as that. And we've also seen a lot of examples of line data being used earlier, especially to show paths of rivers, things like that. And finally, we have polygons. So polygons are created in a similar way to a line, only that the first and last points are joined to make a complete enclosure. And these are used to show boundaries of features such as footprint of a house or a field, an archaeological site boundary or administrative boundaries. Using a building as an example, the position of the shape of the building is captured as a series of 4 pairs of numerical coordinates. And to reproduce the building in a GIS, the computer reads these values and draws a line linking the coordinate points, creating a polygon. Okay, so that's vector data, which is points, lines, and polygons. And now we'll move on to raster data, which is the other data type commonly used in GIS. So you can think of raster data as being similar to a digital photograph, essentially. And this is because it's made up of a grid of same-size pixels, which in GIS we refer to as cells. In GIS, the raster, and therefore each cell of the raster, has a spatial location assigned to it. And each of these cells holds a value which represents a feature as its spatial location. So 2 of the most common file types for raster data are GeoTIFF and JPEG 2000. I say GeoTIFF is way more commonly used and is maybe the most used type of raster data you will see. So while the structure of raster data might seem simple, it's really useful and used for a wide range of applications. A few examples of how raster data are used in GIS is using raster data as base maps, so from images taken from satellites or planes, or those drawn by hand, such as our georeferenced scanned historic maps that we've been using in the MAHSA project. In these cases, the data within each of the cells of the raster image are used to display the colors to create an image. However, raster data can also be used as surface maps that represent data that changes continuously across a landscape, such as an elevation map, as you can see here, where the data in the cells is showing the elevation of that specific cell's location. Or in weather maps, where the information in the cell is showing the temperature in degrees. We can then display these rasters in a way that we feel is good and that looks good, like we've done here. Or raster data can be used for thematic mapping, which can be derived from analyzing other data. For example, here's a simple raster data set that shows land cover classification. So somebody has taken other data sets and classified what the land cover is at that specific location. So in this case, each cell tells us whether that place on the ground is bare ground, whether it's water, or whether it's urban developed areas, which can be really useful to show, the spread of urban sprawl or things like that, or for flooding. So essentially, vector is good for discrete objects, raster is good for continuous surfaces. So as we've seen, information about different locational features are stored as a collection of different files and in different formats. And in a GIS, we can examine all of these together by overlaying this data as layers within a coordinate reference system. This location within the reference system is the key index variable for all of the spatial data. And by having this locational information, a GIS can relate otherwise unrelated information by using location as this key index variable. For example, we can see on the right, we have 4 different layers. The land cover layer you can see is a raster layer because it has the cell. And then we have elevation, parcels, and flood zones, which are vector layers. When they are referenced to a geographic reference system, we can then use all of these together and we can reveal patterns and trends about this area that we may not have been able to see otherwise. Okay. So now we understand how a GIS layers different types of data based on its spatial location within a coordinate reference system. It becomes clear that it's crucially important that all this data must be accurately aligned to real-world locations and also to each other. So therefore, I'm going to talk a tiny bit more about coordinate reference systems, why there's so many of them, and why using the right one underpins the accuracy, the effectiveness, and the presentation of spatial data in GIS. I will rush through this a bit because it can be a bit complicated, but it is important to note. So going back to the image I showed you earlier of the framework draped around the Earth, it may appear that this is very easy to make and to use. However, this nice clean image showing the framework perfectly fitting the Earth, it's disingenuous because actually there's not just one clean framework that's used, but there's many. And the reason because of this is there are 2, and that is the shape of the Earth and the fact that we usually mainly use GIS on 2D screens and not a 3D globe, as you can see here. Both these create issues with precise positioning in GIS, and therefore many coordinate reference systems have been created, and subsequently many ways to project these coordinate reference systems onto a 2D screen have been created. Using the correct coordinate reference system and making sure that your data has been recorded in the correct coordinate reference system are very important in GIS. If we don't use the right coordinate system, our data could be misaligned, and this can create errors in the spatial accuracy of the data. So I mentioned about the Earth's shape. So we first need to understand something simple, that the Earth is not a perfect sphere. If it was perfect or a smooth ball, creating one global coordinate system that we could use for all maps would be easy. But in reality, the Earth is slightly flattened at the poles and it bulges at the equator. So it's also uneven due to variations in gravity and surface mass. I'm not going to explain that too complicated, too much. But essentially, the Earth is not a nice sphere. It's more like a potato-y sphere shape. So it's not nice and clean. It's not a clean geometric shape. And this makes creating a perfectly accurate global framework more complicated. To solve this, scientists use a simplified, smooth mathematical model of Earth, which we call a reference ellipsoid. It's not a perfect representation of the real Earth, but it's close enough to allow us to draw evenly spaced coordinate lines, like latitude and longitude, on top of it. But because it's only an approximation, it won't perfectly match the real Earth everywhere. And you can see from this diagram here, the gray image at the back, that's meant to be the actual shape of the Earth, which is slightly, as I said, a bit like a potato. And the reference ellipsoid is the perfect mathematical model that we define of the Earth that sits on top of it. Some parts of the real Earth don't fit that very well. So you can see some parts stick out and some parts are in a bit. So no model fits the Earth perfectly everywhere. Therefore, there are many different versions of these models that have been created. Some have been designed to fit the whole Earth reasonably well, and others have been designed to fit specific regions very accurately. And the way we align this model to the Earth is called a datum. When we combine this reference ellipsoid, so our model of the Earth, a datum, and latitude and longitude coordinates, we then get what's called a geographic coordinate reference system. And this is why it's important, is that the exact same coordinate numbers can refer to slightly different physical locations depending on which coordinate reference system they are in. So, for example, if someone gives you coordinates, like on the right here, we have a set of decimal coordinates, but doesn't tell you what coordinate reference system they have recorded these in, you may plot them in the wrong place. In some cases, the difference might be small, but in others, it could be hundreds of meters. So we can see an example here. Point A and point B have exactly the same coordinates, but are in different coordinate reference systems. Therefore, we don't know if the real location that the person wants to show us is at point A or is it at point B on the actual Earth. And in previous presentations, for example, in Guili's presentation, she mentioned about stream proximity, which she showed in ranges of 100 meters. For something like this, it's really important to be using the correct coordinate reference system. So if doing analysis like this, if the data of the project coordinate reference system is not one that is suited to that geographic area, then the distances may be wrong. So even if they're slightly wrong, that could have a huge effect on the analysis and therefore what you're trying to show when you're doing making your GIS map. Okay. As well as location, we also need to consider how we will display our map in GIS and how we will display it in 2D. And in general, we look at maps and screens where we have maps on, they are 2D. But coordinate reference systems are in 3D. So it brings another issue, which is flattening these 3D coordinate reference systems onto a 2D plane, or projecting them, which is what we call it in GIS. Projecting is necessary. However, as you can see from this nice GIF, that projecting something that is 3D into a 2D surface is not 100% accurate. If you, for example, draw the Earth on an orange, peel it off, and try and flatten it to 2D, there will be distortion somewhere. You may have to squash down a bit, pull out a bit of it, force it down to be 2D. And that is exactly the same when we take a coordinate reference system of the Earth and put it onto a 2D screen. Therefore, many different projections have been created to show different things. Here are just 6 examples of some popular projections of coordinate reference systems. We have some Mercator at the top left is apparently good for shipping, for navigation of ships, but it's bad to show the correct area. So Antarctica looks huge, where it's really not that big. The Gould-Peters one, which is the second projection, that's good at showing actual area of land, but it looks a bit strange. It looks a bit stretched. Robinson, which is the one in the bottom right, that is actually called a compromise projection, which distorts kind of everything, but not that much. So everything is kind of acceptable, and that's often one that is used. There's just an example of how different coordinate reference systems can distort sizes. So in some, you can see Antarctica is huge, but actually it should be very small. But a fun website to use to see this, the difference in coordinate reference system projections is thetruesizer.com, which you can go on. So hopefully I didn't overcomplicate that, but what I'm trying to say is that the coordinate reference system that you have your data in is really important for what you're trying to show and for the accuracy of the map you're trying to make. We've actually seen a lot of examples already of the use of spatial data within a GIS. And they're all great examples of how to use various layers of data to help understand the world better. So I'm not going to spend too long on this, but I just gave a few examples of how we can take different layers of data in a GIS to create useful outcomes. I always like to put this one first because this is a really kind of historic map that predates GIS, but is exactly how we use GIS. So this is from 1984, and it's a map of locations of cholera deaths in London, and along with nearby water pumps. So you can see that the cholera deaths are the black stack lines. So the bigger the black stack lines, the more deaths in that location. And the water pumps are black circles, which I've highlighted with a blue arrow here. So the data has been layered on top of this map before we've had computers, but this has been done, this has been drawn. And the person who did this, John Snow, can use spatial analysis to see which water pump actually was causing the cholera deaths by layering this different type of point and line polygon data on top of each other. In a more modern example of a very similar thing, this is a map Azadeh actually had in her presentation earlier, and a bit of a plug for the MAHSA project. But we have here we have multiple layers. So sites are shown as points, and districts in Pakistan and Punjab are shown as polygons. The attribute data behind this locational data is used to color the spatial features and to show progress with what we've been working on. So we can color a district green to show that we have completed work on the database in this district, or blue to show that that is in progress. By combining and layering different types of data in this way, the map can quickly and clearly communicate what is happening to the reader. And as the attribute data changes, the map can be updated and new versions can be generated. And what we're going to be doing very soon is a similar thing to this. So changing how data in a GIS looks depending on the attribute data behind its location. In a very similar way to this, and this is always useful because everybody has seen Google Maps. As I said, we often use the product of a GIS all the time without realizing it, and this is what Google Maps is. At its core, Google Maps is created in a GIS, and it combines different layers of spatial data. So roads as vector lines, points of interest as vector points, and features like parks or rivers as vector polygons. And these can all be layered over the top of a raster base map. And they're created to create a clear and readable map. And similar to what I just showed you with changing the colors of the polygons in Google Maps, the vector lines can change color depending on real live data that is coming in. So it's essentially the same thing. The geographic location or the road, the vector line is being changed based on the attribute data that is supporting that geographic data. In more complex examples, this is just an example how people then take many different layers and produce a completely different outcome by using these different layers that are in the same spatial location. So we can use GIS to kind of predict what might happen in the future. So for example, here, potential wheat yield estimates in Punjab in India can be shown here by using various different data. So finally, what GIS softwares are there? Well, there's a number of GIS softwares which have been talked about. And I've just put a few in this picture here, and each have their own advantages and disadvantages. Some are more user-friendly with graphical interfaces. Some can be controlled through predefined tools. Some are better if you prefer writing in code or prefer to use web-based GIS applications. Have a few here. So we have QGIS, which we're going to be using today. Esri ArcGIS, that's one of the most popular ones, but you have to pay for it. We have Python and GDAL there, which are code-based GIS systems. And then we have Google Earth Engine, which has been talked about previously as well, which is an online platform for GIS. But what we're going to be using today is QGIS. And also in potential future practical sessions, we will also be using QGIS So QGIS, it's open source and it's completely free to use. It was first developed in 2002 as an alternative to commercial softwares like ArcGIS and MapInfo, and it's actively maintained and regularly updated. There's many reasons why we're using it, but to keep this short, essentially, first, it's accessible, it's free, and it's cross-platform. Anyone who has a computer and the internet can download and use QGIS without having to pay for it or to obtain a license. Secondly, it's really highly interoperable. It can read and write a load of file formats, making it really compatible with all other GIS systems. And it's extremely powerful, and you can create really good visualizations with it. Finally, and we will touch on this again in the practical, it has a large ecosystem of plugins, which are additional tools that are developed by the GIS community. So you yourself, you can also develop a tool which you can then share with people. Those tools can be used to process geographic information. So finally, before starting the practical session, I just put 3 websites here that if you're interested in QGIS and you like the practical session that we've done, you can have a look at these to get more information about using QGIS.